Okay, so we're looking at 9.2, analyzing rational functions. We've talked a lot about rational functions, what they look like in previous classes, previous lessons. And now what we're going to do is we're going to take a little closer look at rational functions and identify some special characteristics and identify some new terms, okay? And so what I'm going to do is going to kind of skip that intro here, really, and I just want to focus on this equation right here. So if you're looking with me on this page 446, we're going to focus on this right here. So I'm going to flip over to the notes now. And if you want to copy this down, please, it says, consider this function, y equals x squared minus x minus 2 divided by x minus 2. So the question is here, what x value jumps out at you when looking at this rational function? So when you look at this, what x value do you think is of important interest, knowing what we've been studying in this first section of this chapter? 2. Okay, very good. 2. Yeah, x equals 2. That is of particular interest. Now, why did you say x equals 2? Okay, all right, because, okay, you said because it's the asymptote. Okay, now 9.1, we noticed that the x value in the denominator that makes the denominator 0 was an asymptote. This section, okay, we can't assume that right away. And that's the difference between last section and this section. We're going to look at some rational functions where, yes, we have an x value that is a restriction, but it may or may not be a vertical asymptote. Okay? So that's the one little difference. That's what I want to focus on. So I'm really glad you said that. Because you would be right. In most cases, you'd be right. But there are some cases where this is not going to be an asymptote. So what I'd like you to do now, actually, I guess I have the one with the calculator. I'm going to graph this on the graphing calculator. Okay? And we're going to take a look at what this looks like. So here's the function right here, and if we hit graph, it looks like this. Now, we had mentioned that, hey, x equals 2 is of special interest to us. So what is up with x equals 2? We know that x equals 2 is a restricted value, okay? It's restricted, which means that at x equals 2, y is undefined. In 9.1, that translated always into a vertical asymptote. But if we look at this graph again, look at this graph, at x equals 2, which is right here, look at what is going on here. Did I type something in wrong? I don't think so. Let's see. No, I didn't type anything in wrong. So there's something else going on here. And what it is a new type of restricted value. This is called a discontinuity. It's called a point of discontinuity or a gap discontinuity. So what I mean is this, is that if you look at this, what is the value for y when x equals 2? Well, it's something divided by 0. So that doesn't count. But it's not an asymptote. So if I do this, second function calculate a value, and I put in 2, you see it has no y value. Because if we were to zoom in on this, like incredibly, like 1,000 million times, we would see that there's actually one single point that is missing in this line. Just one single point. Now, if we take the values, and this we won't focus on it this lesson, but if we take the values that are really close to 2, like 1.9, okay, the y values for 1.9 would be pretty close to this y value right here. Okay, I want to do close to 3 maybe. 2.01 would also be really close to that same y value, but right at 2 it's restricted. Okay, so let's move on. I know you guys are just dying to find out how this works, right? Yeah, okay, I know. Just waiting with bated breath. Okay, so we go back to the text here. Okay, it says basically graph that, take a look at it. Okay, now I'm going to get to this example right here. And they exaggerate this a little bit, but you see, this is a similar sort of rational function, and it has a gap there. At x equals 3, we have a point that is undefined. Okay? Now, why is that? Well, here's why. Why don't you copy this example down in your book right here. F of x equals, and this will be the second one. We'll go back and take a look at the first one as well. But here's another example. F of x equals x squared minus 5x plus 6 over x minus 3. Okay, so if we take a look at both of these similar functions, what I want to point out to you right now is that the top, the numerator polynomial, in both cases can be factored. Okay? Can be factored into a product of binomials. And the interesting thing is, when we factor this, okay, x squared minus 5x plus 6, we're looking for two, numbers that multiply to 6 and add to negative 5. And that's going to be x minus 2 times x minus 3 all over x minus 3. And for this original example up here too, we can factor this trinomial into x minus 2 times x plus 1 all over x minus 2. So the question is, these are special types of rational functions that do not yield a vertical asymptote, and can you see the common feature that both of them have once we've factored things? What do they look like? What do they both have in common here? Okay, so a factor can be canceled out from, well, I don't like canceled really, but yes, divided out. You're right. It basically goes away. It turns into 1, so it doesn't really disappear. It does not really cancel in a sense, but divided out. Yeah, divided out. I'd like to say that more than cancel. But anyways, you're right. If we look over here, x minus 2 is a factor, can be divided out with x minus 2 on the bottom. Okay? And over here we have x minus 3 and x minus 3. So if we were to simplify this rational function, it simplifies to this. That's our original one. And the second one simplifies to this. Now, if you look at this and you say, well, where did our restriction go? Because now we don't have a restriction. Well, you do have a restriction because the restriction was x can equal 3 in this one and x can equal 2 in this one. It's still there, but it's represented by a gap or a discontinuity, a point of discontinuity. So the bottom line is, in looking at these graphs, if a factor, okay, can be divided out, that is a factor with a variable. If a factor can be divided out from the numerator and the denominator, and there is left no restricted value in the simplified version, that means we have a gap discontinuity. Okay? So we'll write that out in the next slide, get you to write that out in your notes, and but that's what we're talking about. And actually, I'm going to maybe bring up that textbook again, because right here, this is sort of what we'll be kind of going from. I'll summarize this for you, but you can take a moment just to look at that in your textbook as well. Okay, so in your notes, we'll just kind of go from this here. Actually, I'll just zoom in a little bit, so it's a little bit easier for you to see. Whoa, undo that. And move this over. And move this up. Okay, so we'll just go from the textbook here. You can copy out a point of discontinuity. Now, it's a funny word, discontinuity, because you want to say it's discontinuous, but the stress is on the different part of the word, so it's actually not discontinuity, it's discontinuity. The stress is kind of in the middle there. All right? Yeah. I mean, you're not going to fail because of it, but it's, it's like Catholicism. That's what it's like. You don't say Catholicism. You say Catholicism. That's actually how you're supposed to say it. Right? So it's not discontinuity, it's discontinuity. Okay, there's just a little aside there. Okay? All right, so it is a point. Ooh, look at that. Nice highlighter, hey? Now, I'm going to skip over this described by an ordered pair. I actually don't like that at all, because there is no y value. So I don't like the ordered pair. If we're looking for a y value that could be substituted into this point, we have to use the idea of limits, which is coming in calculus. I don't want to get into it now. So it is a point, or you could even say, if we're going to omit this ordered pair thing, you could say it's an x value. okay, at which the graph is not continuous. A point at which the graph is not continuous. That means that it doesn't go all the way through that point. It jumps over that point, okay, or it skips that point. It's one special restriction in the domain, really. Okay, and it occurs in a rational function when the function can be simplified by dividing the numerator and denominator by a common factor that includes a variable. So that is the detailed way of explaining what I just said. You can divide out common factors where there is no variable left in the, well, or where that variable is divided out. So it occurs when its function can be simplified by dividing the numerator and denominator by a common factor or by a factor that includes a variable. There does not have to be, it's not the case where it has to, you can't have anything in the denominator when you've divided. That's not true. But most of the simple ones, there will be nothing left. But yes, you could have, after you've divided out a common factor, you still might have a variable in the denominator. We'll talk about that in a bit. But where one can be divided out, the zero that is associated with that factor is a gap, discontinuity, okay? So it results in a single point that's missing from the graph. A single point is missing from the graph. That's what happens. And we represent that by an open circle. You don't see that on the graphing calculator. The reason is because the graphing calculator, in drawing the line, it uses an infinite number of points, near infinite, now obviously not infinite because it's a finite instrument, but it uses so many points that to take out one, you don't notice it on the screen because of the resolution. That's basically, so that's why it doesn't look like a big fat circle. Okay, but when we're sketching it, we're going to draw a little open circle so that you can communicate that, hey, I know that there's a gap there. That's what that means. Okay? Okay, so if you zoom in on the function, on the calculator, it will show you a little gap in the points. So here's to zoom in, enter. So here it comes. There it is. Wow. It's amazing. Yeah, probably could, but I'm not going to. No. So we could do this all day. Why is the graph straight? Why is the graph straight? Okay, which graph were we doing here? Okay, x minus 2. All right, so this is a x plus 1. It looks straight because we've zoomed in on such a small domain that it actually, you can't really tell if it's going, you know what I mean? Like it's such a small domain there that it just looks that way. It's not actually flat, but if you trace, oops, straight, oh, come on. Okay, forget you. Trace. Okay, see, look at this. It's 1.99999. We've zoomed in quite a bit. And see this? Yeah, this is 2.9999. As we get close here, okay, look at, this is the idea of a limit, you guys. Okay, as we get close to this restricted value, look at what y is doing. What is it coming really super close to? Right. Okay, now look at 2, y is undefined. It's not there. And so if we keep going, look at that, 3.000001. See that? So the limit of the function at this point, and this is calculus terms, this calculus words, the limit of the function as x approaches 2 is 3. That's what it's approaching. Even though at 2 it doesn't tell you anything, it says, whoops. But look at 1.9999867. We have 2.9999867. All right, let's take a look at this example in the textbook. It says compare the behavior of these two functions right here. This one and this one right here. Now they look very similar, but they're different. We have a different sign here, okay? And if you look down below, okay, on the graphing calculator, this is what they look like. This function looks like this, a straight line with a gap right here. This one over here looks a lot more